Okay, so we'll start today talking about homogeneous coordinates and affine transformations. The reason for that is because the first part of the course will be looking at how to calibrate our camera, how to map from pixel coordinates to real-world coordinates. Because that's one of the fundamental problems. It also means, it's also what you need to do before you run any kind of, most kinds of robotics vision pipelines. So when we look at that problem, to begin with, just to give you an idea of where we're going with our we have sort of, anytime we're dealing with computer vision or robot vision in particular, we have this problem that we have some scene of the world, so here we have a car, and now we need to do certain things like autonomous driving. In that case, you may know that for Tesla, Elon Musk's electric car company is pushing very much for fully autonomous driving. They're currently releasing it as a beta upgrade. They use only vision systems, so they don't use any LiDAR scanners or radar sensors on their cars. Elon Musk is very keen on using only vision. So if that's your approach, then let's say you have a Tesla car here that has a camera that can see that car. In order to be able to act reasonable, in order to act intelligently, we need to know certain things, like how far is this car away from the Tesla car, or the intersection, or whatever. Let's say here's another car. Because we need to figure out how far the distance is so we don't bump into that car. We need to figure out which direction it's moving to see whether it's coming at us or driving away from us, those kind of things. Right? So now, with our camera, we get that picture. In order to be able to figure out what the distance is, I need to know something about the 3D geometry. So let's say I have some sort of three-dimensional coordinate system, and our problem is that our camera is only a 2D sensor. If we use a monocular camera, then we only have a two-dimensional representation of the scene. So for humans, how do we figure out distances? Like if I look at this scene here, right? or if you use your eyes now, then from you, how far is it to that wall? Around 2 meters. 2 meters, okay? And how do you know that? How do you know it's not 20 meters or 200 meters or 0.2 meters? Those are all problems that we need to address, right? The geometry of the scene. We need to be able to understand that in order to be able to act reasonable in the physical world. Some robot vision applications, we don't need to know so much about the geometry, like if you're running a machine vision system and you're checking potato chips and you want to count how many potato chips are going through are produced by the company, right? Then you don't really need to know how far away they are. You just need to be able to count 1, 2, 3, 4. But for most of the applications in robotics, the geometry is crucially important, because we need to know if our robots have enough room to drive through there. We need to know whether something is approaching our robot so that they can back off. We can do other things with the vision system to overcome some of the limitations of our sensors, because vision is a very powerful sensor. So we can use the vision system in order to see if our robot is balanced correctly or not, right? If it's upright correctly or not. If it's falling over, we may be able to recognize that with our vision system. So how do humans detect distances? With a single camera, we cannot actually measure distances, right? Because if I have a point here, and later on we'll look at the geometry of the camera, then from my image sensor to this point through the optical center of the camera, I only get a line. So I can only tell the direction, but I cannot tell the distance. So humans, in order to detect distance for things like the pen in front of me, right? If I want to touch these two, then how can I do that? Well, one way I could do it is by knowing where my arms are, right? So that would be using proprioception. However, I don't need to use the arms for that, because you can take a pen and I can still touch the front. So how would I know the distance in that case? It's actually pretty easy for people, because they're very good at vision. In this case, we have two eyes, not just a single eye. So we can use I can use stereo vision. Not all humans. Some people only had accidents, they only have one eye. For them it's a lot harder. Certainly on distances that are small like this. So we use two eyes in the parallax shift in order to be able to measure distances for things that are sort of at arm's length, a little bit further than that. For things like the wall or the door, actually the parallax shift, due to the two eyes that we have, is really not that big. So in order to be able to detect the distance to the door, we use models of the world. I know how big a door is supposed to be, right? So then I can sort of estimate, because the further away the door is, the smaller it'll get, right? I can estimate the distance. Even if I only have one eye, I can still do that. So those are the tricks that humans use, and also what we have to use in computer vision or robot vision in order to be able to reason about the geometry of the scene. At the heart of it, though, is to be able to do this mapping from coordinates in my image to either a line in the real world, or if I have some additional information, I can do things like actually detect the 3D distance. So with our soccer playing robots, we have to track the ball. If I want to track the ball with my robot, then if I only have a single camera, then detecting the width of the ball or the height of the ball is one possibility, but that's quite noisy, very error prone, because the resolution of the cameras on the robots are not very good. So we would get a lot of noise, more noise in the detection of the ball using the size, even though we use that for our soccer playing robot as well. But what we use mostly is that we assume that the ball is on the ground floor. Because right now, the robots, when they play soccer, they always kick the ball, but the ball very rarely actually goes into the air. Most of the time it's rolling on the ground. And because of that, I know one of the coordinates, so then I can figure out what that distance is, what the 3D point is. And that's a problem that we're mostly interested in when we're dealing with robot vision. The other type of problem, of course, is also important. So the inverse of that problem is also important. Not so much for robotics, but taking a pixel coordinate, taking a 3D coordinate, knowing where the 3D coordinate is, and then figuring out where that is in the image, that is completely defined. For every 3D point, there's only one pixel in the image where that can be mapped to. That problem is the problem that we need to solve when we are doing computer graphics. Because in that case, I have a model of the world. I know I want to draw a laptop, and I know what the width and the height of the laptop is, and I know where the laptop is, and then I want to do the computer graphics. Like if you want to work for Hollywood, it's exactly the inverse of the problem that we're dealing with in robots. In robotics, I have an image, right? And I need the robot to figure out that there's a 5-meter path in front of me that I can drive without falling over. But then there's a table, then I have to stop. So I start with the image, and I end up with a model of the world. Hollywood does exactly the other way around. They have a model of the world, they need to know what the image looks like so that they can show it to you in the cinema. So, in the grand scheme of things, that's what we're interested in at the moment. So we start very simple, and we look at what kind of transformations do we actually have when we're dealing with the coordinate system. Now, while we're doing this, we also learn some matplotlib programming. And anytime you're dealing with these kind of 3D problems, it is nice to be able to visualize them and draw them using Matplotlib. The reason is that otherwise it's very difficult to actually think about what will happen. Let's say if my camera shifts to the left, then what happens to the image? Or if the door moves towards me, what happens to the image? It's much easier to sort of think about this and then draw it, generating a visualization of it, and then making sure that your algorithm is working correctly. Quite difficult to do that in your head, especially if you have multiple three-dimensional coordinate systems, because in that case you can sort of think and say, okay, I have a world coordinate system, X, Y, Z, and that moves around, and I have another coordinate system, but this now is a left-handed one, so it's actually going the wrong way. Right? This would be a right-handed coordinate system, so we don't have two right hands or two left hands. It's very easy to get confused. So I like to do drawings, and so one of the useful things to do then is to actually draw errors and also draw the coordinate system. So here we generate a Matplotlib plot where we have a rectangle and a triangle, and they are defined by real-world coordinates. So the rectangle is from 0, 0 to 1, 0 to 1, 2 to 0, 2 to 0, 0. And we have a triangle, minus 0.52, 1.52, 0.54, negative 0.52, and the square with these coordinates. And then I have a function to be able to draw the arrow, which draws the rectangle, the triangle, and the associated square. And I can choose any color I want to draw with this. So now I have a little arrow that I can draw. And it looks like this. So it's located, 0, 0 is here, and then points off. So now I have that shape and I want to first move it around, then what will happen to the coordinates? That's the first problem that we look at. Now I have the shape, but I can think of the shape as a collection of points, and then I only need to worry about moving a single point. And we're dealing with it in 2 dimensions first. So let's take a point, 2, 3. So x coordinate is 2, y coordinate is 3. So here's our point. P 0, P1 minus and let's take a translation. So for 1 So then this is what it would look like. We have a point P, I apply translation to it, then I end up with P dash. The translation is given by T in this case, 4 and 1, or I can change it to 3 and 1, 3 and 2 maybe. Then what's the new x-coordinate of my point? In general, if I have px and tx and py and ty. Not just the numbers. The numbers are just because I drew them. Like I had to put in some numbers so I can draw it. But in general, if I have a point with px, py, and I move it by tx, ty, then what's the new coordinate? Well, this is px, py. Tx, ty is I can plot some more if you want to. So here I have TX. Oh. So now you can try and copy that code and complete the figure drawing the TY. So draw the line from here to there. I can put in the coordinates. And I like to use the format strings in Python, so here's P23. Kx is 3, so now drawing red dashed line from P dash down until you meet this line here. See if you can do that. So you can either copy the entire notebook or just this one cell. Everything you want to do is in that one cell. And I'll be right back. Okay, so next line would be PD1 X would be so dx is 3, ty is 2, and then p dash will be like this. And to make it a little bit nicer, we can use an arrow instead of a straight line. Oh. P0, P1, T0, T1. Oh. So this will be the graphic to show translation from P to P dash. So that means our new coordinates P dash X would be Px plus Tx, P dash Y is equal to Py plus Ty. Now, that's in 2D. In 3D, we have an additional Z coordinate. But other, it stays the same. Now, the reason why we go through this in so much detail is A, to do some drawing using Matplotlib, but also it's important to realize that sometimes these equations you need to know exactly what changes. So right now I'm talking about point P and we move the point. In robotics, sometimes we don't move the points, but we move the coordinate system. The robot moves, but the points stay the same. In that case, the situation would be reversed. Then, if the robot moves to, if I have a coordinate system and here's a point, and here's my camera, right? And the point moves in X and Y direction like this, right? Then it would be Px is plus Tx plus Ty. If this stays the same and I move in Tx, Ty, then now the point is going to go down and to the left. Right? So it's important to realize it's very easy to make a mistake with the sign of those translations and also rotations. You have to be careful to distinguish between situations where the points move. So you're tracking the ball and the robot sits still and you watch the ball roll, right? In that case, it's plus whatever the translation is. If the ball is there and the robot walks up towards the ball, then all of those are going to be inverted. The translations that you apply. So very easy to make a mistake in the sign of those coordinates translations. So translation is one possibility for how points move when either objects move in the world or if the camera moves. Right now we're mostly interested in the camera moving because our robot is moving around and the camera is attached to the robot. So if the camera moves, then we can move the camera by translating it. And we see how that changes the coordinates. Now, The other thing, of course, we can do with the camera is we can also rotate it. So the question is, how do we model the changes to the coordinates if we rotate the camera? How do we model rotation? So we take rotation around the point, and right now we're talking about rotation around the point 0, 0, around the origin. So I have a point, PT, that has coordinates x and y, shown with the red and the green here. Actually, let me change it then. So how do we work out what the corresponding coordinates are of a point that has the coordinates x and y? Then I rotate the point around the origin by angle theta. Then what are the new coordinates of the point? X dash and y dash. So I want to figure out some function of theta that, given a point xy, it returns new points x dash, y dash. Now, as indicated in this particular figure here, taking the 2 points, using Cartesian coordinates, which means xy coordinates, is not so straightforward. So we use an intermediate representation. We convert the points into polar coordinates. Now, polar coordinates are coordinates where the position of the point is defined by an angle with the x-axis, in this case alpha, and a distance r. Right, so this point here would have an angle of 0 degrees with the x-axis and a distance of 6. And this point here would have an angle with the x-axis of 90 degrees and a distance of 4. This point here would have an angle of 45 degrees and a distance of 3. So I can convert from Cartesian coordinates, xy, to polar coordinates, angle alpha and distance r, because the distance would be the square root of x squared plus y squared, and the angle would be the tangent of y, the arctan of y over x, or the arctan of y over x, or the arctan 2 of y and x. So if you want to calculate this function, you have to make sure that you want to use the atan2 function, both in Python or C, C++, any other kind of mathematical program that you write. You don't want to, for new programs, it's a mistake to use atan, really. Otherwise, you have to add a lot more code to check if the line is vertical and which quadrant it lies in. So if you look at this figure, then here's my point PT. Now if I rotate it, then in polar coordinates, the system is much easier, right? Because the new angle is going to be alpha plus theta, and the new distance, the distance to the origin, has not changed. So we end up with R here as well. Right? PT, the distance from 0 to PT is the same as from 0 to PT dash. So if I rotate the point, then in polar coordinates, R dash is unchanged, so it's R, and alpha dash is going to be alpha plus theta. And then we can talk about the fact that then we need to convert from the polar coordinates to Cartesian coordinates again, so that I can express it in terms of x dash and y dash. So x dash would be R dash multiplied by cosine alpha dash, which is R times cos alpha theta plus alpha, and y dash would be R dash times sine of alpha dash, which is R times sine alpha plus theta, or theta plus alpha. And now we can go and look at one of the favorite theorems in mathematics, in geometry, and a very nice proof for it. The question is, what's the cosine of, what's this cosine alpha plus theta, or theta plus alpha? And what's the sine of theta plus alpha here? Well, this you can actually solve. You can actually figure this out using addition theorems for sine and cosine. And then we have this particular figure here. And this is actually pretty nice proof. I want to figure out what's the sine of the sum of two angles and what's the cosine of the sum of two angles. So first, beta, two angles, and I want to figure out if this is unit length, right? So it's the length of 1. Then what's the cosine of alpha plus beta? Cosine would be this. And the sine would be right? Because any unit angle, any unit length vector, this is the cosine, this is the sine. And so now I just do the same thing, except I have 2 here. Right? So I want to find this value. So how do I find that value? Given alpha, beta, well, then I have to look at the other values that I have. So what is this length? From here to there. The sine of, cosine of alpha or beta? Cosine alpha, no. No tangent, no. If this is 1, right, and this is a 90-degree angle, if this is 1, and this is a 90-degree angle here, then this must be cosine beta, right? The length from here. And you know all of this. You know the addition theorems because I'm sure you did them in high school. But I don't, maybe you didn't go through the proof, or you went, if you went through the proof, most of them are algebraic. But I like this geometric proof a lot. It's actually very cool, I think. So this is cos beta, right? So what is this? From here to there. No. If I have this, and I don't have a unit length, right? If this is length R, or K, if this is K, then what is this length? If I have a unit length, this would be cos alpha, correct? If I don't have a unit length, then it would be, yeah? Correct, K, in this case I wrote K, but K cosine alpha, correct, yes. So what is this distance here? How long is this? This from here to there is cosine beta, right? So from here to there would be cosine beta multiplied by cos alpha. right? So now I have the distance, but that distance is too much, right? It's too long. Because I only want this part. I only want cos alpha plus beta. So I need to subtract this part, right? So how do I subtract this part? How big is that? Well, let's look at it. If I draw this part, right? This is what I want to subtract. So what is this length here? From here to there is, if this is cos beta, then this is sine beta, yes. We have a 90-degree angle, unit length, right? So this is sine beta, right? What is this angle? This must be alpha because this is alpha, this is 90 degrees, this is 90 minus alpha, right? 90 minus alpha plus 90 degrees plus this unknown one must be 180 degrees, right? So this must be alpha. So we have sine beta, and this part here is now sine beta multiplied by sine alpha. So that distance here is this distance, this distance is this distance minus this distance, right? So we get cos alpha plus beta is cos alpha cos beta minus sine alpha sine beta, which is, you can look that up in a textbook. But now, even if you don't remember it, you can still prove it. Right? And we can do the same thing for sine alpha plus beta. What would be sine alpha plus beta? Actually, I've shown it already. That would be this part here. Right? So that contains two components. It's this part plus this part. Right? So that part is cosine beta multiplied by sine alpha. And this part here is sine beta multiplied by cos alpha. Because this one is cos alpha multiplied by sine beta. And there you have it. That's the addition theorems for sine and cosine. And this is just the figure to draw exactly that. And here's our Sure. So now I can write that, and I can apply with my addition. I can apply the addition theorem. So cosine alpha plus theta plus alpha will be r cos theta cos alpha minus sine theta alpha, and replacing sine theta plus alpha with sine theta cos alpha plus cos theta sine alpha gives me the second line here. That's replacing it with the addition theorems. And then I can replace cosine alpha multiplied by r. What is cosine alpha multiplied by r? Well, if we look at the original figure, cos alpha multiplied by r is the original x, and sine alpha multiplied by r is the original y. So then I can replace that. Cosine alpha multiplied by r, sine alpha multiplied by r will be x and y. So then x dash will be cosine theta x minus sine theta y, and y dash will be sine theta x plus cosine theta y. Right? So now this is what I wanted. Now I have a function that allows me to calculate the new coordinates based on theta, x, and y. I can now calculate x dash and y dash. But since those two equations are sort of supposed to be applied in parallel, right? I need to calculate both coordinates, x and y. Both new coordinates, x dash and y dash. Mathematicians like to group them together in matrix form. So we can take the rotation operation and convert it into matrix form. So then if I apply my original point as a row vector, a column vector, and multiply it with this matrix, cos theta, negative sine theta, cos theta, then I end up with the new coordinates as a column vector, x dash, y dash. Because x dash is cosine theta multiplied by x plus minus sine theta multiplied by y. And y dash is sine theta multiplied by x plus cos theta multiplied by y, which is exactly the two equations that we have. And this is where it becomes more tricky. Sometimes when you Google, if you forget the equations and you Google for them, sometimes you see them in the other format. Cos, sine, negative sine, cosine. Right? So the minus sign will have moved. And whether this is correct or not depends on what you're moving. It's the same as the translation. If you have a scene and the scene rotates, then the first one is correct. Cos theta, negative sine theta in the first row. If the camera moves and the scene stays constant, then that's the same effect as rotating it in the other direction, right? If I have a point and the point moves from here to there by theta, right? That's the same as taking the coordinate system and rotating the coordinate system by negative theta. So you just have to be careful to make sure that you apply the correct rotation matrix. That you know whether your points move or whether your coordinate system moves. Because one time theta will be positive, the other time theta will be negative. Oh, and usually the rotation is clockwise, counterclockwise, like in mathematics. Like here, positive angle would be counterclockwise rotation of the points, is a clockwise rotation of the coordinate system. So if you look for the rotation matrix, this is the most common form most of the time. If you Google it, most of the results are going to look like this. So now if we want to do a translation by vector, and we want to represent this in matrix form, then we have a problem, because I basically need a constant here, tx and ty. They do not depend on x and y. So if I want to multiply that by a matrix, then I would have to change the value of the matrix for each point that I have, right? Because I'd have to scale it by tx and ty, something like that. So I cannot really have, so far we cannot really have a constant. So if I want to represent this in matrix form, then I want to add a constant tx and ty, but that then has to be multiplied by 1. So I need to extend my coordinates and change them from xy to xy1. Now in theory I could use any other constant as well, but then the tx, ty would change as well. So the simplest one is to just use 1. Now, mathematicians are never very happy with using these kind of irregular matrices. They much prefer to use square matrices. Right? They're easier to deal with. And in particular, the fun thing we can do with them is it's easier to invert them. But by using, so I can convert it to a 3 by 3 matrix where I simply add a 1 to each coordinate, and then I have an extra row 0, 0, 1 here, and similarly for rotation. Right? I simply add an extra 0, 0, 1 there. And a 1 constant. And that gives me then a common representation. Now I can do either translation or rotation. I can represent both, translations or rotations. So another big advantage of having a common representation and a representing the transformation in a 3 by 3 matrix is that now I can also calculate compound transformations. So let's say I have a translation and I take my points and I translate them by 2, 3, tx, ty. Right? Then the corresponding matrix would look in homogeneous coordinates, the corresponding translation matrix, 3 by 3 matrix would look right? So now I take the point and I rotate it by 30 degrees. Then what will happen? So first I translate, then I rotate. I drew this one too early here. Now, after translation, the points are here on the left-hand side, right? That's the new coordinates. So now, if I want to rotate them, I can simply apply a rotation matrix to this. But when I do the calculation, when I do the rotations, then I end up having to left multiply them. Right? We go from right to left. So if I want to rotate by 30 degrees, then it will be cos 30 negative sine 30 0, sine 30 cos 30 0 0 0 1. Right? Now I want to translate it again. Okay, fine, no problem. I can do that. 1 0 dx 0 1 dy 0 0 1. Then I want to do another rotation. Right? And I can keep left multiplying things. However, it's important to realize when we do these transformations and calculate compound transformations, the one on the furthest right is the first one that we did. Right? This is the second, this is the third, this is the fourth. So don't get confused by the order of things. You're more used to reading it this one, then this one, then this one, but that will give you the inverse order, and the result will be different. The compound transformation will be totally wrong then, if you get the order mixed up. So you have to left multiply if you multiply the coordinates. And for later on, we will talk about an extension of this, and you'll see why this becomes important in next class. The homogeneous coordinates here have x, y, 1, right? And that seems to make sense, like that. That's an easy extension to add translations into a matrix representation. Homogeneous coordinates are extensions of this, generalizations of that. And homogeneous coordinates are written as kx, ky, k. Right? So that means I can multiply the coordinate values by any constant, and I just specify what that constant is. So if I have a point, so that means now, since k is sort of a free variable, there's an infinite number of ways in which I can represent a coordinate using homogeneous coordinates. So if I have a point, P is 4, 5, then 4, 5, 1 would be exactly this point, right? But 8, 10, 2 would also be exactly the same point. And -4, -5, -1 would also be exactly this point. And 2, 2.5, 0.5 would also be this point. So there's an infinite number of ways in which I can represent the same point. So homogeneous coordinates have some advantages in theory. One of them is that you can now represent points that are infinitely far away, which you cannot really do using just Cartesian coordinates, because you just end up with infinite or something like that, right? How would I represent a point that's infinitely far away? Well, if k is 0, then 4 divided by 0, 5 divided by 0 would still be the same point, but it would be that point infinitely far away. So that's of interest in more pure mathematics. For robotics and computer graphics, however, the main advantage of using homogeneous coordinates is that it allows us to use a little trick, a little hack, in order to be able to represent all the transformations that I can get with the camera. So if you take out your phone now, right, if you have your phone and turn on your camera and just point it at some place, right? The effects that I can sort of represent now, and you can look at the images, if I move the phone, now I know that would correspond to, in 3 dimensions, it will be a 4 by 4 matrix, right? And if I rotate the phone, then that would also correspond to a 4 by 4 matrix in 3D. Right? So I can do rotation this way, I can do rotation this way or this way. Usually they're called the pitch and the yaw and the roll angles. Right? Or I can move things in 3 dimensions like that. Right? And what the new image, the new coordinates, I would be able to calculate them using a 4 by 4 transformation matrix. What effect, however, can I not model yet using my 4 by 4 matrix? What is happening in the camera image that right now I cannot, it's a little bit hard to visualize, but what effect can I not really model yet? What effect from a camera system can I not model yet by simply moving the points around in the world? If you look at the floor right? You have tiles on the floor, right? If, so far, what we discussed, I can move the tiles further and further, right? What would happen to what happens with the width of the tile in your eyes or in your camera? It becomes smaller, right? But right now, given this 3 by 3 matrix representation or 4 by 4 matrix representation, it wouldn't get smaller. It will stay the same distance, the same length. Because the points would simply be shifted and the distance between the 2 points would remain the same. So that's what's called an affine transformation. That's what we have there. However, camera systems and the human eye, the way that they're built, they also have this perspective distortion, right? Things that are further away become smaller. That's something that we haven't discussed yet. We'll discuss it in the next class. However, homogeneous coordinates allow us a clever way to also deal with perspective distortion. So the last step for a camera system will also be implemented using a 3 by 3 in the 2D case or 4 by 4 in the 3D case. Now, these transformation matrices are at the heart of any kind of vision processing. Homogeneous coordinates and the associated 4 by 4 transformation matrices are fundamental to computer graphics, computer vision, and also a lot of robotics in general because of the kinematics and the inverse kinematics problems. So that's why if you look at any kind of graphics programming package, for example in JavaScript, you have 3GS, which is a JavaScript library for doing 3D graphics. But doesn't matter if it's OpenGL or 3JS or Gazebo if you use ROS, right? All of them, fundamental to them, are 4 by 4 transformation matrices. So I hope they didn't call it something else, but that's the most common way, and any graphics library does the same thing. So we use matrices to encode 3D transformations. Every object has a matrix associated, which gives you the current position. And these matrices are 4 by 4 matrices. And there's a couple of other things, but positioned. We don't actually print them out, but two array, if you get two array, then it will be a 4 by 4 array for the transformation matrix. And it's the same with any other 3D graphics environment. pay money, but okay. So then let's have a look at the other components. Let's do the compound transformation matrices first. So we can define some functions to just generate the corresponding matrices. So for 2D, we rotate around the z coordinate origin. Then our matrix for angle theta would be cos theta, negative sine theta, cos theta, 0, 0, 1. If we translate it, we have 1, 0 tx, 0, 1 ty, 0, 0, 1. And scale and skew, we'll get into that in a second. And then we can apply that to our shapes, right? So here I have my function arrow, which draws the arrow that we had before. And then now I can use the transformation matrices to move that arrow around. So I can rotate it, I can translate it, then I can do a rotation first and then translate it, or I can do a translation first and then rotate it. Now remember, if you look at the code here, if I want to do first, then first I do the rotation, then I do the translation. So it's right to left, and dot is the numpy in order to do matrix multiplication. So this means multiply rot1 by trans1 next. So this corresponds to rotation first, then translation. Here we have translation first and then rotation. And here are the corresponding figures. So we have the original, then I can translate it, and I can rotate it by 90, 130 degrees maybe. And of course I can change that in the code. So here I rotate it by 140 degrees. And also, if you write code for doing these kind of computations, then it's also always a good idea to keep all your angles in radians, because cosine, sine, tangent, all require angles in radians, not in degrees. So if you call cosine 90 in Python or in C or C++ or any other computer language, then you won't get 0, most likely, because it expects it in radians. So to convert from degrees into radians, you have to divide it by 180 and then multiply it by pi. So instead of 0 to 360 degrees, it's much better to always represent your angles from 0 to 2 pi and only print them out. When I print them out, that's when I usually apply the transformation and convert them from radians into degrees. Because when I look at the printout, it's much easier to understand if something is 30 degrees as opposed to 30 degrees would be pi over 2, pi over 4, pi over 5 or something like that. So pi over 2, pi over 6. So then, remember, rotation is always around the origin. So if I translate it first, if I rotate it first and then translate it, then I end up with this yellow figure. If I translate it first and then rotate it, I end up with the cyan figure. So remember that your transformation matrices must be left multiplied. So then we have other kind of affine transformations that are not so important for robotic vision. They are more important for computer graphics. In particular, what happens if my matrix looks like this? 3, 0, 0, 0, 0.5, 0, 0, 0, 1. Then, and here are my coordinates, x, y, 1, then what will happen to the image? No? Scale, yes. So what does it mean? Yeah, it's squash, right? Because here I end up with, this will simply be 3x and 0.5y, right? So if it's before at 1, it'll go to 3. If it's before at 2, it'll go to 6. So before they're 1 unit apart, now they're 3 units apart. So in the x coordinate, I would, if I have this shape, and I apply this transformation, then what I would get would be x is stretched by a factor of 3, y is squashed by a factor of 2. So it'd be this kind of shape. And that one is important for computer graphics, like if you zoom in on something. And the other part is cube. So what does that matrix do? when y is not changed, right? And x will be x plus 2y, which means as y goes up for the points, right, it's going to be shifted towards the right because I add something to the x coordinate. So if before my image looks like this, then after the skew it will look like this sort of thing. It's like the whole thing is slanted over by a certain distance. So those are important for computer graphics. Scaling, of course, to zoom things up and down. Skew is important for rotation, and we'll see in a second how that works. But lastly, let's have a think about this. So far, I can take points and I can rotate them around the origin, right? But what if I want to rotate around this point, not the origin? So I have a point with Rx, Ry. Then how do I rotate around point Rx, Ry instead of the origin? Because if I take this picture and I rotate by 30 degrees, right, the point would end up about here. If I rotate around this point, then the point would end up about here. Right? So I want to end up with totally different points. So how can we do rotation around arbitrary points? Well, that is actually not that difficult once you realize that in order to rotate around point Rx, Ry, what I have to do is first move that point to the origin, then rotate it, then shift everything back, translate everything back to where it's supposed to be. Right? But since we have this nice and dandy matrix representation, I can simply calculate the compound transformation matrices. So first, I take this point, move it to the origin. Right? So that means every point I subtract Rx and I subtract Ry. So now, either way you want to think about it, either you take the whole thing and you move it to the origin, or you take the coordinate system, you move the coordinate system to the origin. It's the same thing. right? The same transformation. Then we rotate. And after that, I need to shift it all back to where it's supposed to be. And this would be the coordinates of the points after rotating them around point Rx, Ry by 30 degrees or theta degrees. Now, these matrices, I can actually pre-calculate them. Right? They're independent of x and y. Which is why we can just calculate that. Compound transformation, then you can store it. If you want to do that to a whole bunch of points, then it's very easy to calculate that, very efficient to calculate that. But remember, we're always using homogeneous coordinates, which means that in 2D we're dealing with a 3 by 3 matrix, not a 2 by 2 matrix. And in 3D we're dealing with a 4 by 4 matrix. And of course I can combine anything here I want. I can rotate around the point, scale it, skew it, either in the x or the y direction. For the skew, there is two versions. 1, 0, 0, ky, 1, 0, 0, 0, 1 is the other one. This will skew along x, and this value here will be skew along y. So then I can muck around with my arrow figure. The blue is the original. Then I can scale it. By 0.5 in x, which means the x dimension will be squashed and the y direction will be extended. So that gives us the yellow figure. And the cyan figure is askew along the y coordinate. And you can see it's not a rotation, right? It's just shifted. It's not actually rotated. This line here is still parallel to the x-axis. So then we can do fancy plots. So we can start with our arrow and then we can keep making it smaller and smaller and applying rotation to it. So you can do some kind of fancy graphics. So I do that by scaling it 80% in the x direction, 110% in the y direction, translating it by 0.5 and rotating it by negative 15 degrees. And I also added a skew to it. So in 3D, as I mentioned, the rotation, the transformation matrices will be 4 by 4. Translation, scaling, and skewing can now take 3 parameters because we can translate X, Y, Z, we can scale in the X, Y, Z direction, and we can skew in the X, Y, Z direction. And for rotation, now we can rotate around 3 different axes, not just the Z axis, but I could also rotate around the X axis or the Y axis. And here's some more arrow figures. Using random transformation matrices. So the point is that now in 2D, any 3 by 3 matrix I can interpret as a transformation matrix. Now I assume that the bottom row is 0, 0, 1, so that one doesn't really count, but I have sort of 6 floating point numbers that I can pick randomly. I get a random transformation of the original shape. So here, if I want to rotate around an arbitrary point xr, yr, then I have to move the point xr, yr to the origin, rotate, and then move everything back. So if I want to rotate around point 0.5, so here's my arrow, 0.5 and 4. If I want to rotate around this point here, then this is exactly what happens. I can take that point, move it here, rotate by 140 degrees, and then shift everything back. So now this is the point where everything rotates around. Oh, but the rotation here is not 140 degrees, it's 70 degrees. So let me change that, 70 degrees. So this is rotation around the origin, this is rotation around this point here. Now let me try and finalize this. Okay, good. And here's another earlier version of the same lecture slides. Okay, so not that easy to run TypeScript in Google Collaboratory. I can run it on my own server, but not on the Google one. So we'll stick with Python. I just want to see if the 3JS library works on the web page. Okay. Oh, yeah, not everything's going to work. Okay, never mind. Okay, good. Then that's it for today. And I will see you again next week.